Welcome back. Today also we will continue the same topic of computation of magnetic field intensity for different current configurations. In the last lecture also we have tried to compute flux density and field intensity due to different line current elements, and we will solve some more problems today. First of all, the very first problem, if you carefully see, it has been asked to develop an expression for the magnetic fields. We feel it as magnetic field intensity at any point on the line through the center at a distance h from the center and perpendicular to the plane of a plane circular loop of radius a and carrying current I. Which means that there is a circular loop. We will take up this one. This is a circular loop of radius radius A, and it is a carrying current of I. And he says that magnetic field at any point on the line through the center and perpendicular to the plane. Okay, which means that there is a line which is passing through the center of this one, and which is at a height h. Okay, so what is the magnetic field intensity at point h? This is what has been asked for us. So these are the terms which have been given for us. One is A, radius of the circular loop, the current flowing in the circular loop, and the distance between the point and the center. And it is being said that the point is on the axis joining the center of the circular loop and in perpendicular direction. Okay, so now let us consider that the wire loop be along xy axis, which means that I'll take this wire loop on xy axis. Okay, this is my x-axis and this is my y-axis. Okay, I'll take this in this fashion, and the schematic diagram this I'm showing, and this is the axis which is joining the center. I'll take it as I'll take my point somewhere here at a distance of h, and this is my radius. Okay, so now I'll consider two diametrically opposite elements of the wire loop, dl and dl dash. So if you consider whatever may be, if I consider a differential element here. Okay, so this differential element, okay, let us consider this is the best way. So this is my loop which is carrying a current of I, and see this is the point. So if I consider dl here, so this will develop a field if I consider dl here, see it will be developing a field in this fashion, right? And it has two components. One is normal component, the other one is a vertical component. If let us suppose this is theta, this component is, I'll assume that this is h1. Okay, this is h1 sin theta, and this is h1 cos theta. Diametrically opposite to this one, there is another element. I'll take it as dl dash. See, it will also be in the same thing. Let us suppose it is developing h2. Now h2 sin theta will be in this fashion, and this is h2 cos theta. So if you carefully see, these components, cosine components, are getting cancelled. They will be equal in magnitude and they will be cancelling out each other. Only the vertical components get summed up. So whatever the components, even if you take here and here, even if you take here and here, every element will be having a diametrically opposite element, and the horizontal components will get eliminated. Only vertical components you will be having. So that's why I will minimize this one into a simple one. So h is equal to, I'll consider only sin theta component. Okay, so what I will be doing now is, this is my general expression, right? dh is equal to I by 4 pi r square into dl ur, right? So dl is nothing but, idl is nothing but my differential current element, and this is my unit vector joining the line from the point to this differential line, correct? Now, so I'll draw only instead of this entire thing. This is my point, right? This is my point P, and this is my L, ideal, and this is my A. I'll take that this is the distance between the differential current element which I'm considering and the point which I'm considering. This is R. Okay, and this is theta. Okay, so what I will do now is my expression now. So this is, so this was actually the earlier slide where we have been considering only sine theta component. So that's why ideal 4 pi r square sine theta component, and you can see that if I consider that this is in xy plane, all the vertical components only I am considering, and they will be in the direction of z plane, right? So that's why this has been modified into this fashion. The earlier equation of h is equal to dh is equal to, this has been modified. I won't consider everything. I'll be considering only ideal sine theta components by 4 pi r square, and the direction will be in z direction only. So this is what this stands for. So in this one, we are trying to make some sense the relation between, this is h, this is a, and this is my current element ideal, and this is the distance r. This is my theta. Okay, I am considering only vertical components only. Okay, I won't consider horizontal components. This is my h sine theta. Only these things will add up for me. Okay, so in this triangle, if you carefully see, these are my standard terms. So what is sine theta now? Sine theta will be opposite by hypotenuse. Hypotenuse is r, and you know that r in this case is h square plus a square. If I substitute here, this will become a by square root of h square plus a square. Right. So my expression now, earlier we have seen that dh is equal to I dl sine theta by 4 pi r square into uz, right? This is my expression, right? So here for sine theta, I will write it as a by square root of h square plus a square. Ideal, I'll keep it like that only. And 4 pi r square is there. Now r square, I'll write it this way. 4 pi, this is r square. Okay. So this is my expression. So if you carefully see, to get the entire field, I should integrate it over the entire length. Right. So this is my entire length of, I have considered only dl here. If I will be, this is my a, this is my h. If I vary the element here, from here to here, if I vary from here, if I take here, well, the value of a, will it change? No, a value will not change. H value also is not going to change. So that's why I am removing these terms. I will not change, a will not change, h will not change. I will remove these terms from the integral. So only dl is going to change. So over the entire length, what is the differential length you are considering? So what is this value? If I consider this as the entire wire, this is nothing but circumference of the wire, right? Circumference of the wire. What is circumference of the wire? It is 2 pi a. So substitute there, 2 pi a. So this is 2 pi a. So what is the final answer? This is my final answer. Okay. Okay. This is the field at point P, which is at a distance of h. If h is 0, then what will this become? This will become, if I get h is 0, this will become 2a square whole to the power of 3. So this will become 2a cube, a square will go I by 2a. This is what we have done yesterday. Okay. So I hope now you have understood how to determine the magnetic field intensity for a ring type of configuration. Okay. Now we'll move on to the next problem now. See, there is a conducting triangular loop in the below figure. It is said that it is carrying a current. Find h at some point 0, 0, 5 due to side 1 of the loop. See, this is a triangle. It has 3 sides, 1, 2 and 3. You want to determine the current only because of this particular side. This side is having 0, 0, 0 because z is 0. Z has not been mentioned anywhere. I'll take it as z is equal to 0. So this is one point and this point is 2, 0, 0. So which means that there is a line current element 0, 0, 0 and it is 2, 0, 0 and at point H, sorry, I'll take it as point P, 0, 0, 5, you need to determine the H at this point. Okay. So what is the, I'll take it as alpha 1, I'll take it as alpha 2. We'll try to solve this problem. Yeah. Considering the triangle, the side 1 has 2 vertices, these are the 2 vertices, and the point is 0, 0, 5. This is the other simplest representation. If you carefully see in this entire component, y-axis is missing. Right? Y-axis is not there, it is just a 0. So that's why I have mentioned only x and y-axis here. Sorry, x and z-axis here. This is z-axis and this is x-axis. On x-axis, I do have these two components. 0, 0, 0, it lies on x-axis. This also lies on x-axis. And this is on z-axis. Okay. Now, this is an easiest problem. We can easily identify this one. You know that the formula is very much simple to determine H. It is I by 4 pi H into cos alpha 1 plus cos alpha 2 into U L bar cross U R bar. We have termed this one as U phi. Okay. So, in this one, what is the current which is flowing? It is 10 amperes. So, I will become 10 amperes. Shortest distance. What is the shortest distance? This is the shortest distance from the point. This is the point, right? Onto the line conductor. The shortest distance is, this is 5, right? We can directly write it as 5. Cos alpha 1, this is alpha 1 and this is alpha 2. Alpha 1 you can directly see it is 90 degrees. Alpha 2 you can compute alpha 2. What is cos alpha 2? Cos alpha 2 is adjacent, this is length is 2 and this hypotenuse is 5 square plus 2 square, it is 29. So cos alpha 2 will be 2 by root 29. Whereas cos alpha 1 will be, what is cos alpha 1? It will be 0 degrees, 0, because alpha 1 is 90, right? So you can't get that one. Alpha 1 is equal to, cos alpha 1 is equal to 0. Now I'll substitute each and everything. Okay. So this is my expression. This is, right? This is unit vector along the line current. And this is the vector which is joining the current element to the point, right? So in this case, what is, we have seen, right? This is x-axis, this was z-axis. This was the point, right? UR was UZ itself. Whereas this one, it was along x-axis. I can directly write this one, right? It is just like ux bar. If you want, you can solve this one. This is 0, 0, 0. This is 2, 0, 0. You can write the entire thing, but I can directly take it as ux bar. So what is now u alpha? Ux star uz and it is minus uy bar. Now I'll substitute each and everything. This is what we have already done. So this is the formula. I is 10 amperes, shortest distance is 5. This will become 0. This will become 2 by root 29. And this is minus uy. If I substitute, this is my final answer. Okay. So the field intensity at 0, 0, 5 due to side 1 is this one. Okay. I hope that now you have been able to compute magnetic flux density for different current configurations, and this is your homework problem. You try to determine the expression of B at any point along the axis of a solenoid. Okay, thank you.